Welcome to this full and free course on analysis of variance, or ANOVA for short. In this video, we'll explore what analysis of variance actually is and why you need it. We'll take a deep dive into the different types of ANOVA, helping you understand when and how to use each one. We'll start with the basics of the One-Way ANOVA, then move on to the more advanced Two-Way ANOVA, ANOVA with repeated measures, and the powerful Mixed Model ANOVA. Throughout, we'll break down the key concepts, assumptions, and calculations, all using simple examples to make it easy to follow along. By the end of this video, you'll have a clear understanding of how to apply ANOVA in your own data analysis. If you like, you will find the content of this video in our book Statistics Made Easy. So let's get started. First of all, as already said, there are different types of analysis of variance. In this video, we'll discuss the One-Way and Two-Way ANOVA, and the ANOVA with repeated measures, and the Mixed Model ANOVA. But to keep things simple, let's start with the simplest and most common one, the One-Way ANOVA. What is a One-Way ANOVA? The One-Way ANOVA is a hypothesis test. Okay, and what does the One-Way ANOVA test? An ANOVA tests whether there are statistically significant differences between three or more groups. More precisely, it is tested whether there is a significant difference between the mean values of the groups. An example: you want to investigate whether there is a difference between fertilizers A, B, and C in terms of plant growth. The analysis of variance now helps you to find out whether there is a significant difference in plant growth between the three groups. But doesn't the t-test do something similar? That's true. The t-test tests whether there is a difference between two groups. The analysis of variance is now an extension of the t-test, and it tests whether there is a difference between more than two groups. So if you only had two fertilizers, A and B, that you wanted to compare, you would use a t-test. If you have three or more different fertilizers, you would use an ANOVA. Okay, that makes sense. What are the hypotheses tested in an ANOVA? In an ANOVA, the null hypothesis is that the mean values of the groups are equal. Mathematically, this can be expressed as μ1 is equal to μ2 is equal to μk, where μ1 to μk represents the mean values of the different groups. And the alternative hypothesis is that the mean values of the groups are not equal. This can be expressed mathematically as follows. At least one μe is different, where E stands for one of the groups under consideration. What are the assumptions of an ANOVA and how is it calculated? Let's look at this with the help of an example. Let's say you are a researcher and you want to find out whether three different drugs have a different effect on blood pressure. So your research question is, do the three drugs have a different effect on blood pressure? The null hypothesis is, there is no difference between the three drugs in terms of blood pressure. And the alternative hypothesis is, there is a difference between the three drugs in terms of blood pressure. In order to calculate an ANOVA, we of course need data. How do we get the data? We obtain data by taking a sample from the population we need to analyze, for example, all people suffering from high blood pressure. Let's say we took a sample of 24 test subjects. We can then divide these 24 test subjects into three groups, with each group receiving a different drug. Okay, but now we still don't have any data, we only have groups for now. That's right, in order to be able to calculate an ANOVA, we have to measure something for each subject, in our case the blood pressure. We measure the blood pressure for each test person once at the beginning and once at the end of the treatment. The difference between the two values tells us how the blood pressure has changed while taking the medication. We have now collected data. But what about the assumptions? We still have to check them, don't we? Exactly, so that you can calculate an ANOVA, these assumptions must be met. Number 1, level of measurement. First, the levels of measurement for your variable must be appropriate for an ANOVA. The independent variable should be nominal, such as the type of medication or the type of fertilizer applied. The dependent variable, on the other hand, must be metric, like blood pressure or plant growth. To summarize, we need a variable that defines the different groups, such as the different medications, and a variable that reflects what is measured in the different groups, for example, blood pressure. But now to the second assumption, independence. The measurements should be independent, i.e. the measured value of one group should not be influenced by the measured value of another group. The third assumption is that of normal distribution. The data within the groups should be normally distributed. This assumption becomes less important as the sample size increases, but should still be evaluated, especially for small samples. If this assumption is violated, the Kruskal-Wallis test can be used as an alternative. If you would like to know how to test data for normal distribution, please watch my video Test for Normal Distribution. And thus to the fourth assumption. The variances in each group should be roughly the same. In other words, it should not be the case that we have a very large variance or a very small variance in one group compared to the other group. This assumption can be tested with the Levene test. You can find more information in my video on the Levene test. If this assumption is not met, the Welch ANOVA can be used as an alternative. Okay, but how does an ANOVA work? We want to know whether there is a difference between the groups. To test whether there is a difference, the ANOVA uses the ratio of the variance between the groups and the variance within the groups. What is the between-group variance and what is the within-group variance? The variance between the groups measures how much the mean values of the groups differ from each other. In our case, the deviation of the mean values of groups A, B, and C. In this case, we would have a big variance, in that case, a small one. What is the variance within the groups? The within-group variance measures how much the individual data points in each group fluctuate. In this case, we would have a large variance within the groups, in that case, a small variance. The ratio between the variance between the groups and the variance within the groups is now the so-called F-value or F-statistic. If the variance between the groups is small and the variance within the groups is large, then we get a small F-value. In this case, it is likely that these deviations or even larger ones occur purely by chance, even if in reality there is no difference between the groups. However, if we have a small spread within the groups and a large spread between the groups, then the F-value is large. It is then very unlikely that such a difference or an even more extreme difference would arise purely by chance. Or to be more precise, it is very unlikely that we will obtain such an F-value or an even larger one. Therefore, to assess whether the differences between the groups are statistically significant, we use the F-value. However, this F-value does not give us a definite answer. To assess the significance of the results more precisely, we need the p-value. So let's calculate the p-value. Let's say this is our data. We have the values from the first, second and third group. So now we start and calculate the variance between the groups and the variance within the groups. First of all, we need the total mean and the mean values of the individual groups. We obtain the total mean by adding up all the values and dividing by the number of values. We have a total of 24 values. This gives us a total mean of 5.3. We get the mean values of the groups by simply adding up all the values of the respective group and dividing by the number of values per group. Now we've calculated all the required mean values and we can calculate the so-called sum of squares between the groups. To do this, we calculate the difference between each group mean and the total mean. Square this and add up the results. N is the number of values in the eth group. So we get 2.5 minus 5.3 squared plus 8 minus 5.3 squared plus 5.5 minus 5.3 squared. The sum of the squares between the groups is therefore 121.3. Now we can calculate the sum of squares within the groups. To calculate this, we subtract the mean of each group from each individual value within that group. So we subtract the mean of the first group from each of its values, the mean of the second group from each of its values, and the mean of the third group from each of its values. We square the differences obtained and add everything up. For example, in group 1, we subtract the group average of 2.5 from the first value, from the second value, and so on. In total, we get a sum of squares within the groups of 36. So now we've almost made it. We've calculated the total mean and the group mean values. We have calculated the sum of squares between the groups and within the groups. And now we can calculate the variances within and between the groups. In most cases, however, the term variance is not used, but mean squares, which we will now also adopt. We obtain the mean squares between the groups by dividing the sum of squares between the groups by the number of degrees of freedom between the groups. We've just calculated the sum of squares between the groups, and the degrees of freedom result from the number of groups minus 1. So in our case, 3 minus 1, which is equal to 2. We get a mean square of 60.67. So now we need the mean squares within the groups. These are obtained by dividing the calculated sum of squares within the groups by the degrees of freedom within the groups. The degrees of freedom result from the total number of values, in our case 24, minus the number of groups, in our case 3, so we get 21. Now we can calculate the F value. To do this, we divide the mean square between the groups by the mean square within the groups. Or if we take the expression from the beginning, the variance between the groups by the variance within the groups, we get an F value of 35.39. But what about the p-value? We can calculate the p-value with an F distribution. To do this, we simply go to datatab.net. We need the degrees of freedom between the groups, in our case 2, the degrees of freedom within the groups, in our case 21, and we need the F value, which is calculated, i.e. 35.39. We get a p-value that is smaller than 0.01. So if we use the usual significance level of 5%, we get a significant difference, and we reject the null hypothesis that there is no difference between the three groups. Of course, you can simply calculate an ANOVA online with DataTab. Just copy your data into this table and click on Hypothesis Test. Then simply select your desired variables, for example, blood pressure and medication. And ANOVA will now be calculated automatically. If you don't know exactly how to interpret the results, simply click on Summary in Words. Or you can simply click on AI interpretation for most tables. In this table, we now get exactly the values that we just calculated by hand. And we can also see here that we get a significant result. As I said, you can simply click on AI interpretation to help you understand the results. Now there's one more topic to cover, the post-hoc test. A post-hoc test becomes necessary when an ANOVA indicates a significant difference between groups. While ANOVA can confirm that differences exist, it doesn't specify which groups are different from each other. A post-hoc test helps to pinpoint exactly which groups differ from each other. It performs a pairwise comparison between the groups, indicating, for example, whether group A differs from group B or group C. In our case, the post-hoc test reveals that all groups differ significantly from one another. However, this isn't always the outcome. It's possible that only group 1 differs from group 2, or that no individual groups shows a significant difference, even if the ANOVA result is significant overall. Now that we've covered that, let's take it a step further and dive into something even more exciting, the two-way ANOVA. What is a two-way ANOVA? A two-way ANOVA is a statistical method used to test the effect of two categorical variables on a continuous variable. The categorical variables are the independent variables, for example, the variable drug type with drug A and B, and gender with female and male. And the continuous variable is the dependent variable. For example, the reduction in blood pressure. So, the two-way ANOVA is the extension of the one-way ANOVA. While a one-way ANOVA tests the effects of a single independent variable on a dependent variable, a two-way ANOVA tests the effects of two independent variables. The independent variables are called factors. But what is a factor? A factor is, for example, gender of a person with the levels male and female, type of therapy with therapy A, B, and C, or the field of study with medicine, business administration, psychology, and mathematics. In an analysis of variance, a factor is therefore a nominal variable. We use an ANOVA whenever we want to test whether these levels have an influence on the so-called dependent variable. You might want to test whether gender has an effect on salary, whether therapy has an effect on blood pressure, or whether field of study has an effect on length of study. Salary, blood pressure, and length of study will then be the dependent variables. In each of these cases, you test whether the factor has an effect on the dependent variable. Since you only have one factor in these cases, you would use a one-way ANOVA. Okay, you're right. In the first case, we have a variable with only two categories, so of course we would use the independent samples t-test. But when do we use a two-way ANOVA? We use a two-factor analysis of variance when we have a second factor and we want to know whether this factor also has an effect on the dependent variable. We would also like to know whether, in addition to gender, the highest level of education has an impact on salary. Or we would like to include gender in addition to type of therapy. Or in the third case, we would also like to know whether the university attended, in addition to the field of study, has an influence on the length of study. Now we don't have one factor in all three cases, but two factors in each case. And since we now have two factors, we use a two-way analysis of variance. So in a one-way ANOVA, we have one factor from which we create the groups. If the factor we are looking at has three levels, for example, three different types of drug, we will have three groups to compare. In the case of a two-way analysis of variance, the group results from the combination of the levels of the two factors. If we have one factor with three levels and one with two levels, we have a total of 6 groups to compare. But what kind of statements can we make with a two-way ANOVA? With the help of a two-way ANOVA, we can answer 3 things. Whether the first factor has an effect on the dependent variable, whether the second factor has an effect on the dependent variable, and whether there is an interaction effect between the two factors. But what about the hypotheses in a two-way ANOVA? There are 3 null hypotheses and therefore also 3 alternative hypotheses. The first null hypothesis is there is no significant difference between the groups of the first factor. And the alternative hypothesis, there is a significant difference between the groups of the first factor. The second null hypothesis is there is no significant difference between the groups of the second factor. And the alternative hypothesis, there is a significant difference between the groups of the second factor. And the third null hypothesis reflects the interaction effect. One factor has no effect on the effect of the other factor. And the alternative hypothesis, at least one factor has an influence on the effect of the other factor. And what about the assumptions? For the test results to be valid, several assumptions must be met. Number 1. Normality. The data within the groups should be normally distributed. Or alternatively, the residuals should be normally distributed. This can be checked with a quantile-quantile plot. Number 2. Homogeneity of variances. The variance of data in groups should be equal. This can be checked with the Levene's test. Number 3, independence. The measurement should be independent, i.e. the measured value of one group should not be influenced by the measured value of another group. Number 4, measurement level. The dependent variable should have a metric scale level. But how to calculate a two-way ANOVA? Let's look at the example from the beginning. We would like to know if drug type and gender have an influence on the reduction in blood pressure. Drug type has the two levels drug A and B, and gender has the two levels male and female. To answer the question, we collect data. We randomly assigned patients to the treatment combinations and measured the reduction in blood pressure after a month. For example, the first patient receives drug A, is male, and after 1 month, a reduction in blood pressure of 6 was measured. Now let us answer the questions. Is there a main effect of drug type on the reduction in blood pressure? Is there a main effect of gender on the reduction in blood pressure? And is there an interaction effect between drug type and gender on the reduction in blood pressure? For the calculation, we can use either a statistical software like DataTab or do it by hand. First, I will show you how to calculate it with DataTab and how to interpret the results. At the end, I will show you how to calculate the ANOVA by hand and go through all the equations. To calculate a two-way ANOVA online, simply visit datatab.net and copy your data into this table. Then click on Hypothesis Test. Under this tab, you will find a lot of hypothesis tests, and depending on which variable you select, you will get an appropriate hypothesis test suggested. We want to know if drug type and gender have an influence on the reduction in blood pressure. So let's just click on all 3 variables. DataTab now automatically gives us a two-way ANOVA. We can read the 3 null and the 3 alternative hypotheses here. Afterwards, we get the descriptive statistics and the Levene test for equal variance. With the Levene test, we can check if the variances within the groups are equal. The p-value is greater than 0.05, so we assume equality of variance in the groups for this data. And here we see the results of the analysis of variance. We'll look at these in more detail in a moment. But if you don't know exactly how to interpret the results, you can also just click on Summary in Words. In addition, you can check here if the requirements for the analysis of variance are met at all. But now back to the results. Let's take a closer look at this table. The first row tests the null hypothesis whether drug type has an effect on the reduction in blood pressure. The second row tests whether gender has an effect on the reduction in blood pressure. And the third row tests if the interaction has an effect. You can read the p-value in each case right at the back here. Let's say we set the significance level at 5%. If our calculated p-value is less than 0.05, the null hypothesis is rejected. And if the calculated p-value is greater than 0.05, the null hypothesis is not rejected. Thus, we see that all 3 p-values are greater than 0.05, and therefore we cannot reject any of the 3 null hypotheses. Therefore, neither the drug type nor gender have a significant effect on the reduction in blood pressure. And there's also no significant interaction effect. But what does an analysis of variance actually do? And why is the word variance in analysis of variance? In a two-way analysis of variance, the total variance of the dependent variable is divided into the variance that can be explained by factor A, the variance that can be explained by factor B, the variance of the interaction, and the error variance. Actually, SS is not the variance, but the sum of squares. We will discuss how to calculate the variance in this case in a moment. But how can I imagine that? The dependent variable has some variance. In our example, not everyone will have the same reduction in blood pressure. We now want to know if we can explain some of this variance by the variables drug type, gender, and their interaction. The part that we cannot explain by these three terms accumulates in the error. If the result looked like this, we would be able to explain almost all the variance by factors A and B and their interaction, and we would only have a very small proportion that could not be explained. This means that we can make a very good statement about the reduction in blood pressure by the variable drug type, sex, and interaction. In this case, it would be the other way round. Drug type, gender, and the interaction almost have no effect on the reduction in blood pressure, and it all adds up in the error. But how do we calculate the sum of squares, the F value and the P value? Here we have our data, once drug type with drug A and B, and once gender with male and female. So these individuals are, for example, all male and have been given drug A. First, we calculate the mean values we need. We calculate the mean value of each group, so male and drug A, that is 5.8, then male and drug B, that is 5.4, and we do the same for female. Then we calculate the mean value of all males and females and the mean value of drug A and B. Finally, we need the total mean. We can now start to calculate the sum of squares. Let's start with the total sum of squares. We do this by subtracting the total mean from each individual value, squaring the result, and adding up all the values. The total mean is 5.4, so we calculate 6 minus 5.4 squared plus 4 minus 5.4 squared to finally 3 minus 5.4 squared. So we get a sum of squares of 84.8. The degrees of freedom are given by n times p times q minus 1. N is the number of people in a group, in our case 5, and P and Q are the number of categories in each of the factors. In both cases, we have two groups. The total variance is calculated by dividing the sum of squares by the degrees of freedom. So we get 4.46. Now we can calculate the sum of squares between the groups. For this, we calculate the group mean minus the total mean. So 5.8 minus 5.4 squared plus 5.4 minus 5.4 squared, and the same for these two values. We get 7.6. In this case, the degrees of freedom are 3, which gives us a variance of 2.53. Now we can calculate the sum of squares of factor A. A dash is the mean value of the categories of factor A. So we calculate 5.9 minus the total mean value and 4.9 minus the total mean value. This results in 5. Together with the degrees of freedom, we can now calculate the variance for factor A, which is 5. We do the same for factor B. In this case, we use the mean values of male and female, and we get the variance of 0.8. Now we can calculate the sum of squares for the interaction. We obtain this by calculating the sum of squares minus the sum of squares of A and B. The degrees of freedom result to 1. For the interaction, we get a variance of 1.8. Finally, we can calculate the sum of squares of the error. We subtract the mean value of each group from the respective group values. So, in this group, we subtract 5.8 from each individual value. In this group, we subtract 5.4. Here we subtract 6. And then we subtract 4.4. This gives us a sum of squares of 77.2. The degrees of freedom are 16, and we get a variance of 4.83. And now we calculate the F values. These are obtained by dividing the variance of factor A, B, or the interaction by the error variance. So we get the F value for factor A by dividing the variance of factor A by the error variance, which is equal to 1.04. We can now do exactly the same for FB and FAB. To verify, we get exactly the same values with data tab: 1.04, 0.17 and 0.37. For the calculation of the p-value, you need the degrees of freedom and the f-distribution. So with these three values, you can either read the critical p-value in a table, or as usual, you just use a software to calculate the p-values. You can find the table of critical f-values on Data tab. E.g., for a significance level of 5%, you can use this table. If the red value is greater than the calculated f-value, the null hypothesis is rejected, otherwise not. Next, we'll explore ANOVA with repeated measures. This approach is particularly useful when the same subjects are measured multiple times under different conditions, and it allows us to account for the variability within individuals. Let's dive into how this method works and when it's most appropriate to use. We will go through the following questions. What is a repeated measures analysis of variance? What are the hypotheses and the assumptions? How is a repeated measures ANOVA calculated? How are the results interpreted? And what is a post hoc test and how do you interpret it? We'll go through all points using a simple example. Let's start with the first question. What is a repeated measures ANOVA? A repeated measures analysis of variance tests whether there is a statistically significant difference between three or more dependent samples. What are dependent samples? In a dependent sample, the same participants are measured multiple times under different conditions or at different time points. We therefore have several measurements from each person involved. Let's take a look at an example. Let's say we want to investigate the effectiveness of a training program. For this, we've started looking for volunteers to participate. In order to investigate the effectiveness of the program, we measure the physical fitness of the participants at several points in time, before the training program, immediately after completion, and 2 months later. So for each participant, we have a value for physical fitness before the program, a value immediately after completion, and a value 2 months later. And since we are measuring the same participants at different points in time, we are dealing with dependent samples. Now, of course, it doesn't have to be about people or points in time. In a generalized way, we can say, in a dependent sample, the same test units are measured several times under different conditions. The test units can be people, animals, or cells, for example, and the conditions can be time points or treatments, for example. But what is the purpose of repeated measures ANOVA? We want to know whether the fitness program has an influence on physical fitness. And it is precisely this question that we can answer with the help of an ANOVA with repeated measures. Physical fitness is therefore our dependent variable, and time is our independent variable, with time points as levels. So the analysis of variance with repeated measures checks whether there is a significant difference between the different time points. But isn't that what the paired samples t-test does? Doesn't it also test whether there is a difference between dependent samples? That's correct. The paired samples t-test evaluates whether there is a difference between two dependent groups. The repeated measures ANOVA extends this concept, allowing you to examine differences among three or more dependent groups. What are the hypotheses for repeated measures ANOVA? The null hypothesis for a repeated measures ANOVA is that there are no differences between the means of the different conditions or time points. In other words, the null hypothesis assumes that each person has the same value at all times. The values of the individual persons themselves may differ, but one and the same person always has the same value. The alternative hypothesis, on the other hand, is that there is a difference between the dependent groups. In our example, the null hypothesis states that the training program has no influence on physical fitness, i.e. that physical fitness does not change over time, and the alternative hypothesis assumes that the training program does have an influence, i.e. that physical fitness changes over time. To correctly apply repeated measures ANOVA, certain assumptions about the data must be fulfilled. Number 1. Normality. The dependent variable should be approximately normally distributed. This can be tested using the QQ plot or the Kolmogorov-Smirnov test. For more information, please watch my video Test for Normal Distribution. You can find the link in the video description. Number 2. Sphericity. The variances of the differences between all combinations of factor levels or time points should be the same. This can be tested with the help of Marshall's test for sphericity. If the resulting p-value is greater than 0.05, we can assume that the variances are equal and the assumption is not violated. In this case, the p-value is greater than 0.05. Therefore, this assumption is fulfilled. If the assumption is violated, adjustments such as Greenhouse-Geyser or Hein-Feld can be made. Now I'll show you how to calculate and interpret an analysis of variance online with DataTab. And then we'll go through the formulas to explain how to calculate the analysis of variance with repeated measures by hand. To calculate an ANOVA online, you simply go to datatab.net and copy your own data into this table. I use this example dataset. You can find a link to load this example dataset in the video description. Make sure that your data is structured correctly, i.e. one row per participant and one column per condition or time. Now we click on the Hypothesis Test tab. At the bottom, we see the 3 variables before, in the middle and end from the dataset. If we now click on all of them, a repeated measures ANOVA is automatically calculated. Firstly, we can check the assumptions. Here we see that the Marshall's test for sphericity results in a p-value of 0.357. This value is greater than 0.05 and thus the assumption is fulfilled. If this is not the case, you can tick sphericity correction. I will explain how to test the normal distribution in a separate video. In our example now, we will assume normal distribution with a lot of gnashing of teeth. If the assumption is not fulfilled, you can simply calculate the non-parametric counterpart to the repeated measures ANOVA, the Friedman test. This does not require your data to be normally distributed. First of all, if you do not know exactly how to interpret the individual tables in your analysis, you can simply click on Summary in Words or on AI interpretation for the tables. But now back to the results. First we see the null and the alternative hypothesis. The null hypothesis is that there is no difference between the dependent variables before, in the middle and end. And the alternative hypothesis is that there is a difference. At the end of the test, we can say whether we reject this null hypothesis or not. Now we see the descriptive statistics and a box plot. We then get the results of the ANOVA with repeated measures. In this table, the p-value is the most important value. It is 0.01 and indicates the probability that a sample deviates as much or even more from the null hypothesis as our sample. With a p-value of 0.01, the results are statistically significant at the conventional significance level of 0.05, which means that there are significant differences between the mean values of the 3 levels before, in the middle and end. This rejects the null hypothesis and we assume that there is a difference between the groups and that the training program or therapy has a significant effect. If you want an interpretation of the other values in this table, simply click on AI interpretation. Finally, here is the table for the Bonferroni post hoc test. Since the p-value of the analysis of variance is smaller than 0.05, we know that there is a difference between one or more groups. With the post hoc test, we can now determine between which groups this difference exists. We see that there is a significant difference between before and in the middle and end. Both have a p-value of less than 0.05. How do you calculate an analysis of variance with repeated measures by hand? Let's say this is our data. We have 5 people, each of whom we measured at 3 different points in time. Now we can calculate the necessary mean values. First, we calculate the mean value of all the data, which is 5.4. Then we calculate the mean value of the 3 groups. For the first groups, we get a mean value of 5. For the second, a value of 6.1. And for the third, a value of 5.1. And finally, we can calculate the mean value of the 3 measurements for each person. So for the first person, for example, we have an average value of 8 over the 3 measurements, and for the last person, we have an average value of 5. Now that we have all the mean values, we need to calculate the required sums of squares. But note, our goal is the so-called f-value, and subsequently calculate a p-value from it. There are different ways for getting this f-value. I will demonstrate one common way how to do this. Depending on which statistics textbook you use, you may come across a different formula. But back to the calculation. Let's start with the sum of squares within the subjects. We obtain this by calculating each individual value xmi minus the mean value of the respective subject, squaring this and adding it up. So we start with 7 minus 8 squared plus 9 minus 8 squared until finally 3 minus 5 and 7 minus 5. We can then calculate the sum of squares of the treatment, i.e. the sum of squares of the 3 points in time. We obtain this by subtracting the total mean value from each group mean value, squaring it and adding it up. N is the number of people in a group. So we get 5 minus 5.4 squared plus 6.1 minus 5.4 squared plus 5.1 minus 5.4 squared. Now we can calculate the sum of squares of the residual. We get this by simply calculating the sum of squares within the subjects minus the sum of squares of the treatment. Alternatively, we can also use this formula. Here, xmi is again the value of each individual person, ai is the mean value of the respective group, pm is the mean value of the respective person of the 3 points in time, and g is the total mean value. We can then calculate the mean squares. To do this, we divide the respective sum of squares by the degrees of freedom. The mean square of the treatment is therefore calculated by dividing the sum of squares of the treatment by the degrees of freedom of the treatment. The degrees of freedom of the treatment are the number of factor levels minus 1. So we have 3 time points minus 1, which is 2. The mean square of the residual is obtained in the same way. Here the degrees of freedom are the number of factor levels minus 1 times the number of subjects minus 1. We get 2 times 7, which is equal to 14. Now we calculate the f-value, which is done by dividing the mean square of the treatment by the mean square of the residual or error. Finally, we calculate the p-value using the f-value and the degrees of freedom from the treatment and residual. To calculate the p-value, you can simply go to this page on Data tab. The link can be found in the video description. Here you can enter your values. Our f-value is 1.69, the numerator degree of freedom, i.e. that of the treatments, is 2, and the denominator degree of freedom, i.e. that of the error, is 14. We get a p-value of 0.22. The p-value is greater than 0.05 and therefore we do not have enough evidence to reject the null hypothesis. Of course, we can then compare the results with DataTab. To do this, we copy the data back into this table and click on the variables. We can see that we also get a p-value of 0.22 here. Now that we've explored ANOVA with repeated measures, let's tackle something that's going to make everything you've learned even more powerful, the Mixed Model ANOVA. We'll discuss the following topics. What is a Mixed Model ANOVA? What are the hypotheses and assumptions? And how to interpret the results of a Mixed Model ANOVA? This is what we discuss in this video. Let's start with the first question. What is a Mixed Model ANOVA? A Mixed Model ANOVA is a statistical method used to analyze data that involves both between subject factors and within subject factors. But what are between subject factors and within subject factors? Let's look at an example. Let's say we want to test whether different diets have an effect on cholesterol levels. We would like to compare the 3 diets A, B and C. So the factor diet has the 3 levels A, B and C. To test whether there is a difference between the diets, we are conducting a study with 18 participants. The individual participants are called subjects. Now we randomly assign 6 participants to each of the 3 groups. Each participant or subject is assigned to only one group. In this case, we have a between subjects factor. Different subjects are exposed to different levels of a factor. In this analysis, our objective is to determine whether significant differences exist in the mean cholesterol levels among the various groups under study. And this is exactly what a one-way ANOVA does. Now, of course, we could also examine the impact of one diet across multiple time points. We could measure the cholesterol levels at each participant at the start of the diet, after 2 weeks and after 4 weeks. So the factor time has the 3 levels start, 2 weeks and 4 weeks. And in this case, the same subjects are being exposed to all levels of the factor. And this is called a within subjects factor. The same subjects are exposed to all levels or conditions. In this case, we want to know if there is a difference in the mean value of the cholesterol levels between the different points in time. And this is exactly what a repeated measures ANOVA does. Therefore, in a repeated measures ANOVA, we have within subject factors. So in a between subjects design, each subject or participant is only assigned to one factor level, so that the different subjects only have the influence of the respective group. In contrast, in a within subjects design, the same subjects or participants are exposed to all factor levels, which enables a direct comparison of the reactions to each factor level. But what if we want to test if there is a difference between diet A, B and C over the different points in time? So we want to test if there is a difference between the diets and if there is a difference between the different time points. Then we need a mixed model ANOVA because we have both, one between subject factor and one within subject factor. So in a mixed model ANOVA, we have at least one between subjects factor and at least one within subjects factor in the same analysis. Note, a mixed model ANOVA is also called a two-way ANOVA with repeated measures, because there are 2 factors and one of them results from repeated measures. Therefore, the mixed model ANOVA tests whether there is a difference between more than 2 samples which are divided at least between 2 factors. One of the factors is a result of measurement repetition. With the help of a mixed model ANOVA, you can now answer 3 things. First, whether the within subject factor has an effect on a dependent variable. Second, whether the between subject factor has an effect on a dependent variable. And third, whether there is a so-called interaction effect between the 2 factors. This gives us a good transition to the hypotheses. The first null hypothesis is The mean values of the different measurement times do not differ. There are no significant differences between the groups of the within subject factor. Then, of course, there is the second. The means of the different groups of the between subject factor do not differ. And the third null hypothesis reflects the interaction effect. One factor has no effect on the effect of the other factor. What are the assumptions of a mixed model ANOVA? Normality. The dependent variable should be approximately normally distributed within each group of the dependent variables. This assumption is especially important when the sample size is small. When a sample size is large, ANOVA is somewhat robust to violations of normality. Homogeneity of variances. The variances in each group should be equal. In mixed model ANOVA, this needs to be true for both the within subjects and between subjects factors. The Levene's test can be used to check this assumption. Homogeneity of covariances, sphericity. This applies to the within subjects factors and assumes that the variance of the differences between all combinations of the different groups are equal. What does that mean? Let's start with the differences between all combinations. To do this, we simply need to calculate the difference of the first group minus the second, the difference of the first group and the third group, and the difference of the second group and the third group. These calculated differences should now have the same variance. This assumption can be tested using Morshley's test of sphericity. When this assumption is violated, adjustments to the degrees of freedom, such as Greenhouse-Geyser or Hein-Feld, can be used. Independence of observations. This assumes that the observations are independent of each other. This is a fundamental assumption in ANOVA and is usually assured by the study design. No significant outliers. Outliers can have a disproportionate effect on ANOVA, potentially causing misleading results. It's important to identify and address outliers. Let's calculate an example and I'll show you how to interpret the results. Let's say this is our data that we want to analyze. We want to know whether therapy A, B, and C and 3 different time points have an effect on cholesterol levels. Each row is one person. The therapy is the between subject factor and the time with the levels before the therapy in the middle and at the end of the therapy is the within subject factor. So, the first patient on therapy A had a cholesterol level of 165 before therapy, a cholesterol level of 145 in the middle, and a cholesterol level of 140 at the end. Let's first calculate the example online with DataTab and then discuss how to interpret the results. To calculate an ANOVA online, simply go to datatab.net and copy your data into this table. You can also load this example dataset using the link in the video description. Then click on Hypothesis Testing. Under this tab, you will find a lot of hypothesis tests, and depending on which variable you click on, you will get an appropriate hypothesis test suggested. If you copy your data up here, the variables will appear down here. If the correct scale level is not automatically detected, you can simply change it under Variables view. For example, if we click on Before, Middle and End, a repeated measures ANOVA is automatically calculated. But we also want to include the therapy, so we just click on Therapy. Now we get a mixed model ANOVA. We can read the 3 null and the 3 alternative hypotheses here. Then we get the descriptive statistics output. And here we see the results of the analysis of variance and also the post-hoc test. We'll look at these again in detail in a moment. But if you don't know exactly how to interpret the results, you can also click on Summary in Words. But now back to the results. Most important in this table are these 3 rows. With these 3 rows, you can check if the 3 null hypotheses we stated before are rejected or not. The first row tests your null hypothesis, whether cholesterol level changes over time. so whether the therapies have an effect on cholesterol level. The second row tests whether there is a difference between the respective therapy forms with respect to cholesterol level. And the last row checks if there is an interaction between the two factors. You can read the p-value in each case right at the back here. Let's say we set the significance level at 5%. If our calculated p-value is less than 0.05, then the respective null hypothesis is rejected. And if the calculated p-value is greater than 0.05, then the null hypothesis is not rejected. Thus, we see here that the p-value of before, middle and end is less than 0.05, and therefore the values at before, middle and end are significantly different in terms of cholesterol levels. The p-value in the second row is greater than 0.05, therefore the types of therapy have no significant influence on the cholesterol level. It is important to note that the mean value over the 3 time points is considered here. It could also be that in one therapy the blood pressure increases and in the other therapy the blood pressure decreases, but on average over the time points the blood pressure is the same. If this was the case, however, we would have an interaction between the therapies and the time. We test this with the last hypothesis. In this case, there is no significant interaction between therapy and time. So there is an influence over time, but it does not matter which therapy is used. The therapy has no significant influence. If one of the two factors has a significant influence, the following two tables show which of the combinations differ significantly. Thanks for watching, and I hope you enjoyed the video.